Welcome to the Deep Dive. Today we're jumping into the really fascinating and frankly fast-moving world of artificial intelligence.
Definitely moving quickly.
Yeah, isn't it? We've gathered quite a stack of sources, foundational Wikipedia pages on AI itself, NLP basics, the history, all to give you a solid, clear picture of what's actually happening.
Just trying to cut through the noise a bit.
Exactly. Our mission really is to pull out the absolute essentials about AI. What are its goals? What techniques does it use? Where is it being applied? And importantly, the ethics. It's surprisingly up and down history and maybe a glimpse at the future.
It's a lot to cover, but yeah, the core ideas.
Think of this as your shortcut, your way to get a real handle on AI without drowning in jargon. Okay, so let's start right at the beginning. What is artificial intelligence fundamentally?
Well, at its core, AI is really the effort to simulate or maybe even create intelligence in machines. That's the big picture.
Simulate or create.
And this broad goal got broken down pretty early on into key challenges, sub-problems. These have really driven AI research ever since the field got its formal start back in '56 at that Dartmouth workshop.
1956? Wow.
Yeah, and these sub-problems are basically the capabilities we think of when we think intelligence.
So things like, what were they aiming for initially? What are those capabilities?
Well, think about the basics. Getting machines to reason, right? To solve problems logically.
Right.
Then, knowledge representation. How do you get a machine to actually store and use information effectively? That's a huge one.
I can imagine.
Planning and making decisions, setting goals, and figuring out how to reach them. Learning, of course, is central.
The ability to improve.
Exactly. Improve over time without someone explicitly telling it every single step for every situation. Then there's natural language processing, NLP understanding, and generating human language.
Like talking to a computer.
Pretty much. Perception, making sense of the world through sensors, cameras, mics, that sort of thing. Social intelligence, which is understanding social cues, interacting appropriately.
That sounds tricky.
It is. And then, for some, the ultimate goal. Artificial General Intelligence, AGI, that's intelligence with the breadth and versatility of a human, not just good at one thing.
Right, the sci-fi version almost. So these have been the targets for, nearly 70 years now?
Broadly speaking, yes. These core areas have guided the research agenda for decades.
Okay, goals established, but how? How do they do it? What are the actual techniques AI uses to tackle these massive challenges?
Ah, right. This is where the toolbox comes in. We can start with something fundamental like search and optimization.
Search, like Google.
Hey, not quite like that. Think more like finding the best route on a map. AI search algorithms explore what's called a state space, all the possible configurations or steps to find an optimal solution.
Okay, exploring possibilities.
Exactly, and there are different ways to do it. Local search looks nearby for better solutions. Evolutionary computation gets ideas from, evolution improving solutions over generations.
Survival of the fittest solutions.
Kinda. And swarm intelligence looks at how ants or bees work together, all ways to navigate huge search spaces efficiently.
So, clever strategies for finding the best answer in a sea of options.
You got it. Then there's logic. Formal logic provides rules for reasoning.
Like math.
A bit like that. Propositional logic deals with true-false statements. Predicate logic lets you talk about objects, properties, relationships, really foundational for making deductions.
Makes sense for structured reasoning, but, the world isn't always logical or certain. It's messy.
Absolutely, and that's where probabilistic methods are crucial. Things like Bayesian networks.
Bayesian, I've heard that term.
Yeah, they're great for reasoning when you don't have all the facts, dealing with uncertainty. You can model probabilities, make predictions based on incomplete data.
That's
Precisely. It's vital for reasoning, learning, planning, even perception when sensor data is noisy. We also use things like Markov decision processes for planning under uncertainty and game theory when multiple AIs or agents are interacting.
Okay, uncertainty covered. Now, machine learning. That's everywhere. How does that fit in?
Machine learning is absolutely central. It's a core technique where programs learn to get better at a task automatically just from experience or data without needing explicit instructions for every scenario.
Learning from data.
Right. And there are different flavors. Unsupervised learning finds patterns in data without labels. just looks for structure.
Like finding groups?
Yeah, or anomalies. Then there's supervised learning, which is probably the most common. You give it labeled examples. This is a cat, this isn't, and it learns to classify new things or predict values. Think ImageNet, that huge database of labeled images.
Right, training data.
Crucial. And then reinforcement learning, where an AI agent learns by trial and error, getting rewards or penalties for its actions. Like teaching a dog tricks, but digitally.
Learn by doing.
Exactly. And I should mention transfer learning too, using knowledge from one task to help learn a related task faster. Very efficient.
Okay, and within machine learning, deep learning, that seems to be the engine behind so much recent progress. What's the difference?
Good question. Deep learning is a type of machine learning, but it specifically uses artificial neural networks with many layers, hence deep.
Neural networks, like the brain.
Loosely inspired by it, yes. These multiple layers allow the network to learn features from data in a hierarchical way. So for an image, the first layers might spot edges, the next layers combine edges into shapes, then textures, then parts of objects, and finally, whole objects.
So it builds up understanding layer by layer.
Exactly. And while neural nets aren't new, deep learning really took off because of two things. Way more computing power, especially GPUs.
Graphics cards.
Yeah, they turned out to be great for this kind of parallel computation. And secondly, the availability of absolutely massive data sets to train these deep networks.
Right, the data and the power came together.
Precisely. And that combination unlocked huge potential, especially in areas like, well, natural language processing, NLP.
Which you mentioned earlier.
Yes. Modern NLP uses techniques like word embedding, turning words into numbers, basically, that capture meaning. And the big breakthrough was the transformer architecture around 2017.
Transformers, not the robots.
No. This architecture allowed models to really understand the context, how words relate to each other in a sentence, weighing their importance. It's the basis for models like GPT.
The ones that write text.
Exactly. Generative pre-trained transformers. By 2023, they were generating incredibly coherent text, even passing tough exams at human levels. Quite remarkable.
It really is. Okay, so that's language. What about seeing and hearing? How does AI perceive the physical world?
That's machine perception. It uses sensors, cameras, microphones, radar, LiDAR to interpret the environment.
Eyes and ears for the machine.
Essentially. This includes computer vision, which is analyzing images and video, speech recognition, obviously, recognizing faces, objects, tracking them over time, and robotic perception, which is critical if a robot needs to navigate or interact with the world.
And it's even trying to understand emotions.
Yeah.
Social cues. That seems like a huge leap.
It is. That falls under social intelligence and effective computing. The idea is to recognize, interpret, maybe even simulate human emotions and social behavior.
Like those customer service chatbots that sound empathetic.
That's one application, yes. They might analyze your text for sentiment or your voice for tone, but it's important to be realistic here. While AI can do sentiment analysis or classify facial expressions to some degree, truly understanding the nuances of human emotion and social context, that's still a very, very hard problem. We're not there yet.
A long way to go on that front.
Definitely.
And all these pieces, the reasoning, learning, perception, language, they're all building blocks, potentially, towards that ultimate goal you mentioned right at the start, AGI.
That's the idea for many researchers, yes. Artificial general intelligence. A machine that isn't just good at one narrow task, but can understand, learn, and apply knowledge flexibly across a wide range of problems, much like a human can. That's the hypothetical endgame.
Wow. Okay, that's a fantastic tour of the AI toolkit. So now let's pivot. Where is all this actually being used? What are some key applications we're seeing make a real difference right now?
Oh, the applications are spreading like wildfire. Let's start with health and medicine. It's a huge area.
Yeah, I hear a lot about that.
AI has massive potential there, helping doctors diagnose diseases earlier, more accurately, personalizing treatments based on your specific data. It's also becoming essential for crunching the enormous data sets in medical research.
Like analyzing genes or...
Exactly, or complex biological structures like in organoid engineering and drug discovery that's being revolutionized.
Right.
So AI algorithms can sift through potential drug candidates incredibly fast. They've helped find potential new antibiotics, candidates for Parkinson's treatments, speeding up the initial screening process by like 10 times and cutting costs maybe 1,000-fold. It's dramatic.
That's incredible, saving time and money in research.
Huge savings. And think about protein folding, understanding how proteins get their complex 3D shapes. DeepMind's AlphaFold 2 basically solved a problem that stumped scientists for decades, predicting protein structures in hours instead of months or years.
Game-changing for biology. Okay, What about outside of medicine? Games, math.
Well, games have always been a testing ground for AI, right? Since the early days.
Yeah.
Beating chess masters, Go champions like AlphaGo did, it's a benchmark for problem solving.
Right, like Deep Blue and Kasparov.
Exactly. In mathematics, we're seeing large language models, LLMs, being used more and more. They show surprising ability with mathematical concepts, even generating proof sometimes.
Wow, but aren't they prone to making things up? Hallucination.
They are, absolutely. That's a big caveat. They need specific training on math problems and reasoning steps to be reliable. But we are seeing specialized models like Qwen2 Math or Microsoft's R-star Math using advanced search techniques, achieving really high accuracy on tough math benchmarks.
So they're becoming tools for mathematicians, but need careful handling.
Precisely. Finance is another big one, though our sources don't detail specifics here. It's a major application area for prediction, fraud detection, trading.
Makes sense. And the military.
Oh, yes. AI is being integrated quite heavily there, enhancing command control, communications, sensor analysis, intelligence gathering, logistics, cyber operations.
Across the board.
Pretty much. And autonomous systems, of course, drones, vehicles. AI helps with things like threat detection, identifying targets, coordinating actions between different units in real time.
It really sounds like it's becoming fundamental infrastructure in many sectors.
It really is. And we have to mention generative AI again, the LLMs and image generators we talked about. Creating and modifying content, text, images, audio, code that's exploded recently.
Yeah, that's hard to miss.
Then there's the general idea of agents, any system that perceives and acts. That ties back to planning and decision-making. And even fields you might not immediately think of, like agriculture.
Farming. How?
Optimizing irrigation, fertilizer use based on sensors and weather data, robotic harvesting, predicting crop yields, detecting diseases or pests early using computer vision.
Precision agriculture?
Exactly. And astronomy. Analyzing the floods of data from telescopes, classifying galaxies, finding exoplanets, predicting solar flares, even helping analyze signals like gravitational waves.
So from farms to deep space.
Yeah.
It's incredibly broad. Our sources also list sexuality, though without specifics.
Yeah, it's noted as an application area in the broader AI landscape, even if these particular readings don't elaborate. It highlights just how pervasive AI is becoming.
Okay. Looking back at this field, it sounds like it wasn't a smooth ride. You mentioned AI winters. Can you walk us through the history a bit, the ups and downs?
Oh, definitely not smooth. It's been very cyclical. So as I mentioned, it formally starts in 1956 at Dartmouth. The mood then was incredibly optimistic.
They thought they'd crack it quickly.
Some really did. Herbert Simon, Marvin Minsky, pioneers, made predictions in the 50s and 60s suggesting human-level AI was maybe only decades away.
But it proved harder than expected.
Much harder. They ran into huge obstacles. One was the combinatorial explosion. Even simple-sounding problems could lead to an astronomical number of possibilities to check. Early AI focused heavily on symbolic reasoning and search, but it just didn't scale well.
Couldn't handle real-world complexity.
Right, and this led to the first AI winter around the mid-70s to early 80s. Promises weren't met. Funding agencies like DARPA got skeptical. Influential critiques like the Lighthill Report came out.
So the plug got pulled, essentially.
Funding dried up significantly, yeah. Also, Minsky and Papert's book, Perceptrons, Analyzing Limitations of Simple Neural Nets, was kind of misinterpreted by some as proving all neural nets were a dead end, which didn't help that approach.
But it bounced back in the 80s.
It did. The early 80s saw a comeback, fueled mainly by the success of expert systems.
What were those?
AI programs designed to mimic human expertise in narrow domains. Like the R1 system at DEC, which configured computer systems and saved them millions. That tangible success brought back funding and optimism, the second AI boom.
Okay, so practical applications brought it back.
Yes, but then came the second AI winter in the late 80s, early 90s. The limitations of those expert systems became clear, and the market for specialized AI hardware, Lisp machines, collapsed. Another reality check.
Another cycle of boom and bust. What changed after that? What led to the current era?
Well, during the late 80s and 90s, researchers started exploring different paths. There was a move towards subsymbolic methods. Rodney Brooks championed building intelligence from the ground up through robotics and interaction with the world-embodied intelligence.
Less abstract, more physical.
Exactly. And crucially, there was a revival of interest in connectionism neural networks. People like Hinton, LeCun did foundational work showing they could actually work for practical tasks, like recognizing handwritten digits.
So the seeds of deep learning were sown then.
They were. Alongside that, you have soft computing gain ground, things like fuzzy logic, evolutionary computation, and probabilistic methods like those Bayesian networks we mentioned, with Judea Pearl being a key figure. New tools for handling uncertainty.
Okay, so diverse approaches were bubbling up.
Yes, and all this set the stage for the massive boom we're in now, the 2010s and 2020s. Driven overwhelmingly by deep learning breakthroughs, like AlexNet in 2012 winning a major image recognition contest.
That was a turning point.
A huge one. Then the transformer architecture in 2017, leading to the powerful LLMs like ChatGPT that just exploded into public view.
And fueled by the computing power and data we discussed.
Exactly. The perfect storm of data, algorithms, and hardware. Plus big successes like AlphaGo beating the Go World Champion in 2015, IBM's Watson winning Jeopardy! In 2011, these captured the imagination.
So massive investment, huge public interest now.
Unprecedented levels of investment, yeah. And a surge in AI jobs. But also, significantly, growing concerns about risks, ethics, fairness, bias, AI safety, leading to serious discussions about regulation.
We definitely need to talk about the ethics.
We do. And it's worth noting, even the Nobel Prizes in 2024 recognized AI's impact, awarding work foundational to AI in physics and chemistry.
Right, so it's gone from niche academic field through Winters to mainstream science and industry with Nobel recognition. Quite a journey.
It really has been.
Before we dive into ethics, maybe just briefly touch on the philosophy. What are the deeper questions AI forces us to ask?
Yeah, the philosophy of AI gets pretty fundamental. It asks, what is intelligence, really? How do we even define it, let alone replicate it?
The definition itself is tricky.
Very. And it evaluates the different approaches. Symbolic AI, or Joe F. AI. Good old-fashioned AI was good at logic puzzles, but famously bad at common sense or seeing things, which are easy for us. That's more Vex paradox.
Hard things are easy. Easy things are hard for AI.
Kind of, yeah. Critics like Hubert Dreyfus argued Joe FAI missed the importance of embodiment, intuition, or unconscious skills. Then you have debates about neat versus scruffy methods, formal logic versus more pragmatic, data-driven stuff, and of course the big one, consciousness.
Can machines be conscious, sentience, have minds?
Exactly. These are huge philosophical debates touching on computationalism is the mind, just computation and functionalism. And now we're even seeing the beginnings of discussions about AI welfare, AI rights, as systems get more complex.
Profound questions about what it means to be intelligent or even alive. Okay, let's tackle the ethics. This feels incredibly important right now. What are the major concerns?
They are numerous and significant. Let's start with risks and potential harm. Privacy is a big one, especially with generative AI trained on vast amounts of data, sometimes including copyrighted material or personal information scraped from the web.
Right, where's the training data come from?
That's a huge issue. Then there's the concentration of power. A few tech giants, Google, Amazon, Microsoft, Meta, Apple, control much of the cloud infrastructure needed for large-scale AI.
Dominance by big tech.
Yes. And related to that, the sheer power consumption. Data centers running AI are energy hogs. The IEA forecasts their electricity demand could double by 2026, potentially reaching the level of Japan's entire usage.
Wow. That's staggering environmental impact.
Absolutely. It could drive up fossil fuel use unless we find clean energy sources fast. You see big tech pursuing nuclear power deals, Amazon buying a nuclear power data center. It's a major challenge.
Okay, power, privacy, what else?
Misinformation. AI can generate fake text, images, videos, deep fakes at scale, making it harder to know what's real.
Undermining trust.
Big time. Then there's algorithmic bias and fairness. This is critical. AI learns from data, and if that data reflects societal biases, the AI will learn and perpetuate them.
So biased data leads to biased AI.
Exactly. We've seen examples in facial recognition struggling with darker skin tones, like Google Photos notoriously mislabeling Black individuals as gorillas due to unrepresentative training data. It can lead to discrimination in loan applications, hiring, housing, even policing.
That's deeply concerning.
It is. And fairness itself is hard to define and implement. There are different kinds, distributive, representational, procedural, and they can conflict. Plus, detecting bias often requires looking at sensitive attributes like race or gender, which runs up against anti-discrimination laws in some places. It's thorny.
A real knotty problem. What about transparency? Understanding why AI makes a decision.
That's the black box problem.
Yeah.
Especially with deep learning, it can be incredibly difficult to trace the exact reasoning behind an AI's output.
Then you get an answer but don't know how it got there.
Right. There was a case where a skin cancer detection AI learned to classify images with rulers in them as cancerous, because rulers were often present in photos of malignant moles used for measurement during training, not because of the mole itself. Or AI misclassifying asthma patients' risk because it learned that asthma sufferers often got better care and thus appeared lower risk in the data.
Dangerous errors from opaque systems.
Yes, and this leads to calls for a right to explanation for significant algorithmic decisions. Then you have the risk of misuse by bad actors.
Weaponized AI.
That's part of it. AI tools can be useful for authoritarian surveillance, cyber attacks, spreading propaganda, and lethal autonomous weapons killer robots raise huge ethical alarms about accountability, escalation, and civilian casualties. There are ongoing UN discussions about potential bans.
The potential for harm seems enormous.
It is. AI can even design novel toxic molecules. And finally, technological unemployment.
AI taking jobs.
The risk is real, particularly for routine cognitive tasks. Think paralegals, maybe some content creation, even fast food cooks with advanced robotics. Some argue it might increase demand for care-related jobs, but it definitely raises ethical questions about mass redundancy and whether certain human roles should be automated even if they can be.
So a whole minefield of ethical issues.
It really is, covering everything from bias and privacy to existential risks and the future of work. It requires careful navigation.
Absolutely. And looking at briefly, what about the far future? Superintelligence, the singularity?
Our sources mention these, yeah. Superintelligence AI, vastly smarter than humans, and the singularity, that hypothetical point of runaway technological growth. These are more speculative, long-term ideas.
Maybe beyond the scope of today, but out there.
Exactly. Concepts like transhumanism enhancing humans with tech are tied into this too. And decomputing, perhaps suggesting a move away from pervasive tech, is also listed as a future topic, interestingly.
A lot to think about for the future. Okay, let's try to wrap this up. We've covered a huge amount of ground. What are the main takeaways people should hold on to from this deep dive into AI?
I think, firstly, understand that AI is driven by this really ambitious goal, creating intelligence. Secondly, it uses a diverse, complex, and rapidly evolving toolkit of techniques, search, logic, probability, machine learning, deep learning.
Not just one magic bullet.
Not at all. Thirdly, its applications are incredibly broad and already transforming society, from medicine and science to industry and our daily lives. Fourth, the history shows it's complex, with hype cycles and hard-won progress.
Ups and downs.
Definitely. And fifth, crucially, it raises profound ethical and philosophical questions about bias, fairness, privacy, the future of humanity, and even the nature of intelligence itself. These demand our attention.
It's clear AI isn't just science fiction anymore. It's here, it's powerful, it's advancing incredibly quickly, and there's huge investment pouring in.
Absolutely. It's a defining technology of our time.
So maybe the final thought for you, the listener, is this. Given how fast this is all moving, and the deep ethical questions it raises, what does intelligent truly mean? And what responsibilities do we have individually and collectively as AI becomes woven ever more tightly into the fabric of our lives?
That's the core question, isn't it? Something to really ponder as we watch this field continue to unfold. It certainly invites reflection and maybe digging deeper into the parts that sparked your interest today.
Indeed. Well, thank you for joining us on this deep dive into artificial intelligence. We'll catch you on the next exploration. Okay, let's unpack this. CSS. It can feel like you're just styling a web page, maybe changing some colors, fonts. Simple enough, right?
Yeah, at first glance, maybe.
But then you try to get things to line up just so, or, look consistent across different devices.
And suddenly you're just drowning in properties.
Exactly. Wondering if align cells is the same as align items and why your beautiful design just imploded on your phone.
Happens to the best of us.
So if you've ever felt like CSS was, well, a bit more complex than it seemed, you're definitely in the right place.
Mm-hmm. And what's really fascinating, I think, is that underneath all those properties, CSS is fundamentally about layout algorithms.
Algorithms, not just styling rules.
Yeah, think of it less like a shopping list of styles and more like instructions for the browser, how it should actually arrange everything.
Okay, I like that framing. And that's really our mission for this deep dive, isn't it?
Pretty much.
To go beyond just listing CSS stuff and really try to get the logic underneath. We've pulled together quite a few sources.
Yeah, articles on core ideas, accessibility, animation tricks, preprocessors.
Responsive design, even a bit of CSS history, a real mix.
A good spread.
And the goal is to pull out those key principles, the why behind the what's, so you can approach styling with, hopefully, a clearer head and maybe less frustration.
Sounds like a plan. So where should we start? Maybe with that fundamental idea you mentioned.
Yeah, let's do that. The idea that the same CSS property can act totally differently depending on the layout mode it's in.
Right. Take width, for example. You'd think width. 2000px always means 2000 pixels wide.
Seems logical.
But as one source points out, that's really only a hard rule in, like, the default flow layout.
The normal way things stack up.
Exactly. Put that same element with width, 2000px, into a flexbox container.
And things change.
It might shrink or grow, depending on the flex settings. It's not an absolute command anymore.
Okay, so the layout mode is like the context, the environment, and the CSS properties react to that environment.
Precisely. It's like the algorithm is the function, and our CSS rules are the arguments